Okay, this is number 1 in section 1.8. So we're doing acceleration velocity models. And so I'm just going to, again, start with problem 1. It says the acceleration of a Maserati, which is just a sports car, is proportional to the difference between 250 kilometers per hour and the velocity of this sports car. So it's given information. So we can definitely translate that first sentence into a differential equation. So let's go ahead and do that before I finish reading the problem, because it's hopefully you guys can see it. So the acceleration we know is, so let's just call it A. Well, we know A is acceleration, but I mean, they're giving us, they're talking about velocity in this case, so we want to express A as dv dt, which we know, hopefully, I mean, from section 1, we know that the derivative of velocity with respect to time is acceleration. So I'm going to go ahead and write dv dt, right, is, so the acceleration of this car is proportional. So definitely have a constant of proportionality, let's just call it K, is proportional to the difference. Okay, so difference in mathematics means you're going to subtract two values. The difference between, so 250 kilometers per hour, so we'll go ahead and put 250, and the velocity of the sports car. So let's just go ahead and write V. So here is our differential equation, right, first order differential equation. And now if we read the second sentence, if this machine can accelerate from rest to 100 kilometers per hour in 10 seconds, okay, so that's more given information. So again, every problem has, right, every application has a given and a goal. So given information, so we have, well, the car is at rest. Well, we definitely know V of 0 is equal to, okay, 0. Let me go ahead and write this and then explain. And then we have V of 10 is equal to 100. Okay, so if this machine can accelerate from rest to 100 kilometers per hour in 10 seconds, okay, that's this part right here. And, well, we know, I mean, this guy here, this is when the car is at rest, right? It's not moving. Right at, t equals 0, at 0 seconds, the velocity is 0. So we have a ton of given information, right? We have our differential equation, and we definitely have our some conditions here, some initial conditions. So we obviously have an initial value problem. So what's the goal? The goal is, well, what's the question? It says, how long, so we're looking for time, will it take for the car to accelerate from rest to 200 kilometers per hour? So let's go ahead and write our goal down. So given and goal. And so we can paraphrase. I mean, that's really asking when. So that last, that question is, when will the car reach a velocity of 200 kilometers per hour? And we can translate that mathematically to V, right, of t is equal to 200. And I shouldn't write, I mean, we're looking for that time, because otherwise I'm saying the velocity function is only 200, which is not true. So at what time, when will the car reach a velocity, right, of 200 kilometers per hour? So that is, I mean, that's really the challenging part, to construct your differential equation. You're given, right, initial conditions, and then of course the goal. So this is a nice review of, I mean, really 1.1 through 1.7, and how you want to solve this differential equation. So let's go ahead and let me write that down again. So I have dv dt is k times this quantity. And let's see, we have v and t. This equation's definitely, this is going to be separable. Separable. And let's see, I'm going to go ahead and multiply dt to both sides. And let's see, so if we get dv equals k times this quantity, dt. And let's see, I want my v's. Okay, so I'm going to divide by this guy. So 1 over 250 minus v, we can even write the dv here, equals k dt, right? So definitely separable. And I'm going to go ahead and just hit dot, dot, dot. So I'll continue this in the next video just to keep it short so the uploading doesn't take too long.